Good afternoon, everybody. Hopefully you've had a chance to get started on the do now. We're starting with exam 3 review. So after this, there's going to be a couple more questions that we'll go through just to shake the cobwebs off of chapter 5 and do a quick review of chapter 6. So what we'll do here is I'll go to the next slide where I have a piece of a periodic table, and I'll go over the answer for these three. Then we'll keep it moving with exam review. We need to use noble gas electron configuration to describe the neutral atom iron, and then we have two ions. We'll start with the iron. Iron is in N equals 4. It's within the D block. If it's in N equals 4, then we need to use the N equals 3 noble gas. So the one that comes right before iron. That's argon. Then we have to fill in everything between argon and iron. So that's the 4s. And 1, 2, 3, 4, 5, 6 electrons in the 3D. So that's for iron. I'll switch to red for phosphorus. Phosphorus is in group 5A. So when it forms an ion, it's going to gain 3 electrons and it'll have a 3 negative charge. That's what we see, P3 minus. If it gains 3 electrons, that means we're starting with 15 electrons and adding 3 more. It's going to look like the noble gas in its row. And remember, these are the noble gases. So we're going to jump 1, 2, 3 to argon. So if you add 3 more electrons, that's a total of 18 electrons, which means that P3 minus looks like argon. The final one, we'll do purple. We're looking at strontium. It's in group 2A. So when it becomes an ion, it's going to lose 2 valence electrons. If we're starting with 38 electrons and we lose 2, that means that we go back 1, 2 to have a total of 36 electrons. And it will look like krypton. Any questions here? Okay. Good. Then we'll move on with our review. I'll give you a couple of minutes to read through this question and put up an answer. And then I'll go over it. Okay. Hopefully you've had a chance to read it. You can put your answer up if you'd like. I'm seeing folks say C. I agree. I'll go over it just to make sure we're all on the same page. This is a chapter 5 question. And the topic is predicting physical properties. In order to predict a property, whether it's chemical or physical, all of the elements have to be in the same group. And they are. They're in group 6A. We know something about the atomic radius of sulfur. and tellurium. We have no idea about selenium, except that it's in group 6A and it should follow a trend. Without doing any math, you should know that the atomic radius should fall somewhere between 104 and 143 picometers, simply because it has to fit that trend. So you can rule everything else out and choose letter C without doing a drop of math. If that kind of logic doesn't make sense to you and you want to see the math, then here's what you do. You find the difference between sulfur and tellurium. That difference is 39 picometers. We're going to say that selenium is going to be about halfway in between. So we're going to take the radius for sulfur and add half, which 39 is pretty close to 40. So I'm going to call it 20 here. Makes the math a little bit easier. We're going to add half of the difference to the radius for sulfur. And that should be the radius for selenium. So I know a few of you got this answer. Let me know if this makes sense to those of you who maybe didn't get it or didn't have time. Okay, thank you. I know everybody doesn't work at the same pace, and unfortunately class favors those who work faster. So I try to wait as much as I can. Now we're doing some chapter 6 review. Classify and write the chemical formulas. So 2 parts. I'll give you your choices for classifying. Binary ionic compound, ternary ionic compound, binary molecular, binary acid, and ternary oxyacid. Those are your choices for classifying. Do that, and then write the chemical formula. I'll give you 3 minutes, then I'll check back in. So this question, we've got to classify and write chemical formulas. We'll start with classifying. So you can put that in the chat if you got that far. We're just going to classify A, B, and C. First one, zinc carbonate. How do we classify it? All right, we got all the answers. Give folks a minute to kind of catch up here. We'll start with the first one. I agree. Zinc carbonate, that's a ternary ionic compound. Remember that those have a metal plus a polyatomic anion. In this case, it's carbonate. For B, it's a binary ionic compound. It's got a metal plus 1 nonmetal. C is a binary molecular compound. It's got 2 nonmetals. There's the classifying part. Now we're going to write the chemical formulas. For a ternary ionic compound, we've got the cation and the anion. For zinc, it's a transition metal, but it's an exception, so there's only one cation that it forms. That's zinc 2+. Carbonate, since we know it's a polyatomic anion, you look at that table and you find that carbonate is CO3 2-. If I have one zinc ion and one carbonate ion, I get 0 as my net charge. So that means my chemical formula is zinc carbonate, just one carbonate ion, okay, one of each. Tin 4 chloride. Tin 4 tells us what its cation is. Tin is SN, 4+. Boom. Chloride comes from chlorine, so we know our element is Cl. It is in group 7A, and to figure out the charge on the anion, we're going to take the group number 7, subtract 8, that gives us 1. So it's a -1. If I took 1 tin and 1 chloride, I would not get 0. So I have to do my swapping trick. The last one is probably the easiest. It tells you everything you need to know in the name. Nitrogen tells you it's the first element, N. Di means 2. Pentoxide. Ox means oxygen. Pent comes from penta, means 5. Questions on these? Alrighty. That's all we're going to do for exam review. The exam 3 review is already posted. The answer key is posted. If you have questions, if you need to meet with me outside of office hours, you can always send me a course message, or you can just talk to me right after class and set something up. My Wednesday morning is filling up pretty tough, so if you need Wednesday morning, you need to tell me now. I also do Thursday morning. I have a couple of slots available for Thursday morning. I also teach on Thursdays, so I've only got like 2 available appointment times. I'm going to use this opportunity to remind you, for the first time, of exam 3. I'll remind you again at the end. There's going to be an exam 3 folder that magically appears tomorrow at about 9 a.m. And it will be available through Friday, March 19th at 11:59 p.m. Inside that folder, You will have a periodic table, as usual, and the common ion sheet. So all those polyatomic anions, all of those will be on that table. You can print both of them out and use them on the exam. Any questions about how to find the exam, what you can use on it? You don't really need a calculator, but you can use one. You can have one if you want it. Okay. So that's exam 3. It's on chapters 5 and 6. For the rest of the course, because we're halfway through, we're doing chapter 7 today. It's on chemical reactions. All things go according to plan. We should get out of here early. Then we're going to do chapters 8 through 10 over the next few weeks. We're going to take 2 weeks for each of those chapters because they're pretty math heavy. I want to make sure that we get enough time to practice problems in class. For those chapters, you will have, chapter check-ins, since you won't have Mastering Chemistry due every week. And that'll give me the opportunity to give you some feedback on how you're doing. So expect at least chapters 8 and 9 to have a chapter check-in. And that's just so you can do some practice, see where you stand, and then practice some more. The final exam schedule is out. And I wanted to make sure that everybody knew. Our final exam time is Tuesday, May 4th at 2 p.m. So it's the same time as class time. And what we'll do is during that time, you'll log in and take your exam. So you need to log in at some point between 2 and 4 p.m., start your exam. So if you usually work during that time, make sure you're not working on that day. I also get the question, since we just had midterms, oh no, is there extra credit though? Yes, there is. Mastering Chemistry. There's something called the Chemistry Primer. That covers all the topics that we have covered and everything we will cover by the end of the course. It is extra credit. It has been available all semester. It will continue to be available until midway through finals week. So your final is on Tuesday, May 4th. Wednesday, May 5th at 11:59. It goes away because I need to do your grades. So you can literally work on it up until that time. It will help you with studying for the final, and you can get back some of those points that you lost on Mastering Chemistry if you missed an assignment or you didn't do as well on 1 or 2 assignments. It'll help you recover some points. Any questions about logistics? We got exam 3 going on, final exam, this is the time. Extra credit, there is some, it's on Mastering Chemistry. Let me know if you're ready to start chapter 7. One more question for you. As always, I try to offer you a break during the class. You usually choose to just keep going if I offer you a break or finishing early. So I'm going to ask you now, y'all want to have a break somewhere, or do we just want to go straight through? I figured. I have not had a class yet that has said, nah, give us a break. Everybody want to go straight through, and then you can go do what you got to do. So I understand. I appreciate it. I like it too. So let's go. If we if we stay on task, we can get done early. Like early. Chapter 7 is not that big. We'll start with evidence for chemical reactions. There's 4 observations that indicate a chemical reaction is taking place. You don't have to see all 4 for it to be an indication of a chemical reaction. You just need a good one. First one you might see is a gas being produced. You got somebody older in your family, your nana or somebody, your pop. Sometimes you be having some stomach issues. You get an Alka-Seltzer out. You put that big white tablet into some water. You see lots of fizzing. That's a chemical reaction. You're dissolving something. You're generating some hydrogen gas. It could be light fizzing, just a few bubbles, or it could be like crazy fizzing. But the release of gas is shown by bubbles. So that's one way that you can tell a chemical reaction is taking place. Second piece of evidence that you might see. An insoluble solid is produced in a solution. So let's say you have 2 aqueous solutions. An aqueous solution is just something dissolved in water. We take them, we add them together, and then all of a sudden you see a solid. That solid is called a precipitate, and it shows that some chemistry happened. So in this image on the right, you've got this yellow liquid forming as you're adding dropwise one aqueous solution into another. If I'm going too fast, let me know. I covered these in the YouTube video, and we also talked about these in chapter 3. So I'm going through them. It should be review. Third one, permanent color change. Oftentimes the transition metals, when they're in solution, they have really pretty colors. If you take 2 clear solutions and you mix them together and all of a sudden it's green or it's blue or something like that, then it's evidence you've made something new. Last but not least, an energy change is observed. What that means is you have a reaction that's releasing heat or absorbing heat. If you're releasing heat, then your reaction vessel, which I always go for a flask because that's the easiest thing to write, easiest thing to conjure, your flask is going to get hot. That's an exothermic reaction, and you'll need to know that term, exothermic. If your reaction absorbs heat, then that flask is going to get cold. That's an endothermic reaction. Again, you'll need to know that term. Release heat, exo, absorb heat, endo. And you can literally tell if you have your hands on your flask or your beaker, you can feel something heating up or cooling off, which is kind of strange, you know. It's not on a hot plate or anything, but if you add some things together, they'll just release heat. And sometimes that flask can get really, really hot, so you have to be careful. So let's do a game show, chemical reaction or not. I'll read one off, and you can tell me in the chat, chemical reaction, excuse me, or not. Okay. First one up. Toasting bread in a toaster. Chemical reaction or no? We've got both answers. It's a chemical reaction. I'll tell you why. When you toast bread in a toaster, that heat is causing changes to the proteins and carbohydrates on the surface of the bread. So you're changing the structure and you're creating something like you can smell it, right? You see that it's starting to brown and it tastes different. So that's actually chemical reactions going on. Number 2, dry ice sublimes. Chemical reaction or nah? Nah. Sublimes. That's a throwback to chapter 3. Sublimation describes the process of a solid going directly to a gas. Dry ice is solid carbon dioxide. You sit that at room temperature on a lab bench or something, you'll see it start to kind of look wispy smoke. It's not a chemical reaction, it's just the carbon dioxide gas forming. And it's so cold, you can kind of see the wispies. So this is actually a physical change. It's a change of state from solid to gas. Third one, 2 clear liquids are combined to give a purple liquid. Yeah, this one's a super easy one. It's a chemical reaction. You got 2 clear liquids, all of a sudden something's purple. That's a permanent color change. Chemistry has happened. These are the types of questions you'll need to answer for your homework and for exam number 4. We good here? Excellent. So we're going to move on from talking about how you can observe a chemical reaction to writing chemical equations and writing written descriptions of those equations. So we got a couple of things we need to talk about first, then we'll get to writing chemical equations in words. First thing, there's a table of symbols that you're going to see in chemical equations. You need to recognize them. The reactants, which are the ingredients, are on the left-hand side. Then there's an arrow, which just means produces or yields. Then you have the products, always on the right-hand side. If you've got more than one reactant or more than one product, they're going to be separated by a plus sign. Sometimes you'll see a little triangle over that yield sign. That just means you need heat for this reaction to occur. It's like the tip of a Bunsen burner, okay? It's the flame. You may also see something like iron or platinum or some other kind of metal. That means you need a catalyst. A catalyst is not consumed during the reaction, but it's present to accelerate it. You might see NR for no reaction on the product side. We'll talk about that a little bit more as we get into talking about the types of chemical reactions. So just put that kind of in your back pocket. Hold on to it for later. Then we've got all the states of matter. When you're writing a chemical equation or you're writing a written description, you have to include the states of matter. We need to know, is this an aqueous solution? Is it a solid? Is it a gas? What are we working with here? So always, always, always include that information for every compound in the equation or your written description. Can I move on from this slide? You're going to need some of this stuff, but I'll kind of remind you as we go through. So let me know if I can move on. The other bit of information that you'll need is to know which elements are written as two atom molecules, which are called diatomic molecules. Those molecules are hydrogen, nitrogen, oxygen, fluorine, chlorine, bromine, iodine. So you got hydrogen off on its own. It's usually kind of in its own little world because it's so different from everything else. All the other ones form a 7 in the periodic table, starting with nitrogen over to fluorine down to iodine. When you're writing a chemical equation, these elements appear as diatomic molecules. So hydrogen gas, you would write H2. Oxygen gas is O2, etc. You'll need to know these. Now we're going to get to the good stuff. Writing a chemical equation in words. First thing you have to do is remember all your chapter 6 knowledge, because we have to take chemical formulas and write their names. We're going to add on a few little nuances here and there, but for the most part, this is all stuff that you should know. First, we're going to name these. CO with an S behind it, that just means that you have solid cobalt. You can write that as cobalt metal or solid cobalt. So whenever you just see one element and then solid, it's likely a metal. So you can write metal. Or to play it safe, just write solid and then the element name. O2, that's oxygen. It's oxygen gas with the G behind it. The last one, we can classify that. We've got a metal plus a nonmetal. It's a binary ionic compound. Cobalt is a transition metal, so we need to figure out its charge. But we know it's going to be cobalt with some kind of charge that we will put as the Roman numeral, followed by the word oxide. We've got 3 oxygen or oxide ions. They each have a -2 charge. I'm not going to go into how we get there because that was chapter 6. If that's something that you're like, wait a minute, I don't know that jump, you can let me know and then we can talk about it right after class. Or you can just revisit chapter 6. We've only got one cobalt. We've got 2 cobalts here. So that means 2 times whatever our charge is for cobalt has to be equal but opposite of the charge from all the oxide ions. So our charge has to be a +3 because that would give us a +6. So we've got cobalt 3 oxide, and it's a solid. We haven't actually answered the question yet. We still have to write this equation in words. We named everything, so we're off to a good start. You start with the reactants, which are on the left-hand side. Solid cobalt and oxygen gas. Oops. are combined, and we see this little triangle here, so that means there's heat. With heat, to produce, you could say to give, to produce, to yield, up to you. Solid cobalt 3 oxide. That's how you would write that in words. And as long as you have the names correct and all the states of matter, the verbiage about, are combined with heat, as long as you mention heat and they're combined somehow, mixed, combined, whatever, then you're good to go. So our solid cobalt and oxygen gas, that's here. Are combined with heat, that was our yield sign with the triangle. It's a delta sign. And then we have the products. That way you can kind of track where each thing came from. How do we feel about this, writing chemical equations in words? We ready to try one? So I'm going to give you one that's a little bit more complicated, but you can name every one of these compounds. Name each compound, take note of its state of matter, and write out this chemical equation in words. I'll give you a head start of about 2 to 3 minutes, and then I'll get started. I'll get started here with naming all of these compounds, and then I will write out the description. So those are all the names of the compounds. Again, if you need help with that, I'm here for you. Just don't have the time in this class because we're trying to cover chapter 7. But if we finish early and people have questions, more than welcome to stay for a little bit and we can go over some things. Now we've got to write out the actual description. A little bit wordy, but here we go. We've got aqueous solutions of lead 2 nitrate and lithium chloride Those are our reactants. Are combined to yield, that's our arrow. And then we've got our products. I said lead 2 chloride precipitate, which is the same as saying solid lead 2 chloride. Precipitate means an insoluble solid. And aqueous lithium nitrate. So as long as you had all the names correct and you had states of matter for everything, some kind of phrase that says they're mixed to yield, combined to produce, or something, then you're good to go. So let me know how we feel about this. We good? Need practice? How's it going? So we'll do one more in this same kind of area before we move on to the next topic. We're going to go in reverse. Take the written description, write the chemical equation. I'll give you 2 minutes to read this through and try to write it out. Then I'll write it out. I'll get started with writing everything out here. First, I'm going to highlight all of my pieces. We've got our reactants there. That's our arrow. And then we've got the products. Aqueous solutions of lithium iodide and silver nitrate. Lithium iodide, silver nitrate, mix to give, that's my arrow, silver iodide precipitate, again that means a solid, and aqueous lithium nitrate. Pretty straightforward. So let me know how we're doing with this. So I'll tell you that for this kind of, you like this way better. Don't worry. Well, the only thing I think that the hardest part of Chapter 7 is balancing equations, and that's not really very hard. So Chapter 7 is pretty smooth. Enjoy it. Chapters 8, 9, and 10 are usually the ones that students find the most difficult. So just giving you the warning now. But it's okay. I hope that I can make it a little bit better, a little bit easier. For Chapter 7, for these types of questions where you have to write the chemical equation or the written description, it's going to be multiple choice or fill in the blank, that kind of thing, matching. You won't have to write it out, like type it out in the exam. It's not a spelling exam. It's making sure that you recognize all the bits and pieces that need to go into the description or the chemical equation. So there, what you really need to do is pay attention to detail. Because I could give you an option where it's the right compounds, but maybe instead of putting solid here, I put aqueous. And that wouldn't be correct. So pay attention to detail. States of matter, make sure that your chemical formulas are correct, all those kinds of things. So we talked about chemical equations, the evidence for chemical reaction. Now we're going to talk about some types of chemical reactions. These are the 5 that we're going to cover. We're going to talk about all of them, related topics, and then I will give you a cheat sheet. That will be very helpful when you're doing your homework and studying for your exam 4. So here we go. First one up, combination reactions. You may also see this referred to as a synthesis reaction. Same thing. You're taking simpler substances, combining them into something more complex. I gave some examples of the types of things you might see as combination reactions, where you have a metal and oxygen gas, or a non-metal and oxygen gas, metal and a non-metal. Those are just examples of combination reactions, and I talk about those more in the video. So if you want specific examples, you can go to the YouTube video. The key is what I wrote at the bottom, and this will be what I put on the cheat sheet. Multiple simple substances or reactants makes one complex product. That is a synthesis or combination reaction. Now, if you're trying to jot stuff down, you can let me know that you need me to wait. Otherwise, I'm going to cut through these a little bit fast just so we can get to balancing equations. We have some other topics to cover too within the types of reactions. So this is pretty straightforward. Second type, decomposition reactions. With a decomposition reaction, you're taking a single complex compound and breaking it down into multiple simpler substances. So it's like the reverse of a combination reaction. Oftentimes you need heat to kickstart a decomposition reaction. Not absolutely a requirement, but oftentimes you'll see it. There's an example here of heating mercury 2 oxide and making mercury metal and oxygen gas. If you're writing this out, you can say produces, right? But you could also say decomposes with heat to yield or to give, something like that. So that's a little bit more phraseology that you can use when you're writing your descriptions. If it's a decomposition reaction, you can say decomposes with heat. You don't have to, just giving you more options. So the take home here, one complex reactant, multiple simpler products. Could maybe use some heat. Third type is single replacement reactions. You have a more active metal displacing a less active metal in a compound. Our example here, we've got iron solid that's being added to a solution of copper 2 sulfate. The iron is this rod here, and it's got that, shiny gray. But on the bottom of it, you see brown. That brown is actually copper. And what happens is, since iron is more active than copper. The iron replaces the copper in solution. So you dissolve some of the iron and it's hanging out with the sulfate ions, and the copper gets kicked out. Get your bags and go. So it's actually plated onto that iron nail. Now you may be thinking to yourself, okay, so iron is more active than copper. How do I know that? I'll tell you how. The activity series. You do not need to memorize this. I will provide the activity series on the exam. What this does is give you the relative activity of all these metals. This is not all the metals on the periodic table, but these are the only ones that we're concerned with. Lithium is the most active. It will replace everything. Gold is the least active. It will replace nothing. It will be replaced by everything. We also have hydrogen here in parentheses. Hydrogen isn't really a metal. It's a little weird, right? But the reason hydrogen is here is because hydrogen is usually it's a part of water and acids. And some subtypes, if you will, of single replacement reactions involve aqueous acids and metal or water and metal. I talk about those specifically in the video. You don't need to know, exactly what an aqueous acid displacement is or an active water displacement. Just understand the concept of single replacement and that hydrogen falls into that. So some metals are more active than hydrogen and they can replace the hydrogen in acids or water. So let's do a little practice with the activity series. We're going to choose the active metal, the more active metal in each pair. Now we talked about iron and copper on the last slide, but I'll show you where they land on the activity series. Iron is here. Copper is here. Iron comes before copper, so iron is more active. Now I want you to look at the chart and tell me which one is more active, strontium or potassium. We'll circle these in red. Strontium's here. Potassium is here. It comes before strontium, so potassium wins. What about lead and nickel? Which one's more active? There's nickel. There's lead. Nickel comes first, so it is more active. So you'll see some questions like that. But we can get a little bit more complex. And we can ask some questions like, will cadmium replace iron in the following reaction? And I've got the reactivity series below. I've got solid cadmium. I'm adding that to a solution of iron 2 nitrate. What I do here is I look up the two metals. I've got cadmium. I've got iron. In order for replacement to happen, the cadmium has to be more active, so it has to come first. Is cadmium more active than iron? Yes or no? No, it's not. Iron comes first. To complete this equation, you would write NR for no reaction. So if you remember that table with all the different symbols you might see in a chemical equation, that's where the NR comes into play. You mix two things, nothing happens. No reaction. I want you to look at the second one. Will zinc replace lead in the following reaction? Yes or no? Here's zinc. I'm using purple for this one. And here's lead. Zinc has to come before lead in order to replace it in solution. The answer is yes, it absolutely will replace it. But what will the products be? We've got zinc here. And then we've got the lead 2, which is part of the lead 2 nitrate that's aqueous, right? With the replacement, the zinc is going to take the place of the lead. So instead of lead 2 nitrate, we now have zinc nitrate. And the lead is off on its own. Does everybody see that? How I completed that equation? Since zinc was more active, I swapped places. You'll need to know how to do that too. You'll definitely see it on the homework and the exam. All right, good. We are moving right along. Double replacement reactions. You can probably guess what happens here. You've got two things switching, but you also make an insoluble substance. So here, what we see, let me switch back to my black. We've got barium chloride and potassium chromate, two aqueous solutions. You add one to the other, and you get ion switching. The barium, instead of being with the chloride, is now with the chromate. The potassium switches partners too. Instead of being with the chromate, it's with the chloride. You must make something that's insoluble. So it could be a precipitate, or maybe it's a gas. Either way, you have to make something that's not an aqueous solution. And that is the key for a double replacement reaction. But in the back of your mind, you're probably saying, if you haven't watched the video, okay, so that's not soluble. How do I know that? I've got a chart. Solubility rules. These are solubility rules for ionic compounds. It's broken up into two parts. The first half, we're talking about things that are generally soluble. So if you see an ionic compound that has the metal ion, lithium, sodium, or potassium, or if you see the ammonium ion, it's going to be soluble. If you see the acetate ion, the nitrate ion, it's going to be soluble. Halides, going to be soluble, but there are some exceptions. I will highlight those exceptions in angry red. Silver, mercury 1, lead 2. Any of those combined with chloride, bromide, or iodide, insoluble. That's an exception. Sulfates, mostly soluble, except for strontium, barium, and lead 2. They are insoluble. That's why they're in angry red. Second half of the chart, we're talking about things that are insoluble, which is really slightly soluble or very slightly soluble. But by and large, you're not getting this to dissolve in water. Not very much of it. Carbonates, chromates, phosphates, sulfides, hydroxides, all those things, insoluble, except if you have one of the ions that are listed in Rule 1. So if I had lithium carbonate, it would be soluble because lithium is a Rule 1 exception. If I had lithium chromate, soluble, Rule 1 exception. But if I had, say, calcium carbonate, insoluble, it's not an exception. All of the exceptions here, I'm highlighting in green for go because they're soluble. If you are a person that likes colors, I recommend you do this because sometimes the exceptions, it gets fuzzy in your brain, like, okay, it's an exception, so does that mean it's soluble or does it mean it's insoluble? And the red means stop, green means go. You can equate with red means insoluble, green means soluble. Don't memorize these. I'll give them to you. But you need to practice how to use this table. And that's exactly what we're going to do next. I'll do the first one with you, and then I want you to do the second one. We have to figure out if tin 2 chromate is a soluble or insoluble compound. And we're talking about soluble in water. I look at the name, tin 2 chromate, and I identify an ion that I see on my solubility rules chart. Chromate. That's on here. It's in Rule 7. And chromates are generally insoluble. The exceptions are Rule 1. I look and see if I have anything that's in Rule 1. Ammonium, lithium, sodium, potassium. None of those are tin 2. So this chromate compound is insoluble. Does the logic for how I broke that down using the solubility rules make sense? I want you to try it on your own with the second one, lead to acetate. And you can let me know in the chat. I'll give you a minute. Soluble or insoluble? Use a S or a I. Or you could type out the whole word because you're fast and smart. You can be slow and smart too. Speed ain't everything. I'll do this one in a different color. We'll do blue. So I'm agreeing with y'all. This one is soluble. The ion that I recognize is the acetate ion. That's rule number 2. And acetates are generally soluble. There's no exceptions. Let's try some more. You know I gotta make it a little bit more difficult. This time, we have 2 aqueous solutions. We're gonna mix them together and predict whether or not the products are soluble or insoluble. I'll walk through this one, then I have another one for you to try. We need to swap our ions. The calcium is with the sulfide. When we combine them, when we combine our 2 solutions, that calcium is going to say, hey, you know what? I want to try the nitrate out. I'm not going to put a state of matter yet because I don't know. The zinc is going to try out that sulfide. So that's how we swap. But that's not the end. I need to ask the question, is calcium nitrate soluble? And is zinc sulfide soluble? I recognize NO3 as nitrate. I find the rule that talks about nitrates. Generally soluble. Cool. So I'm going to put aqueous there. If it's soluble, it's going to dissolve in water. There you go. Sulfides. That's rule 9. They are generally insoluble. Let me check my exceptions. Calcium, strontium, barium, and rule 1, which is ammonium, lithium, sodium, or potassium. None of those are zinc. So that means this particular sulfide compound is insoluble. Put an S there. It forms a solid. Because we had a swapping of ions and we formed an insoluble solid, this is a double replacement reaction. If, however, I didn't form anything that was insoluble and it was just 2 aqueous solutions, I would put no reaction here. You have to form a solid or a gas or something in order for you to have a double replacement reaction. I'm going to let that simmer for a few seconds. And then, if there's no questions, I want you to try one. So I'll wait like 10 seconds. Let it sink in. If you have a question, you can say wait while you type it. Otherwise, I'll move on. So here's the one I want you to do. Now, I didn't do the work of giving you the formulas. I want you to practice. So you'll need to write out what the chemical formulas are for these, and then predict whether or not your products are going to be soluble or insoluble. I'll give you 2 minutes to get started, then I'll jump in and start. Okay, let's write out what these compounds are. We've got lead 2 acetate, and sodium sulfate. We have to perform the swap. We make lead sulfate. Don't yet know what the state of matter is, but I'll leave some space. And we have sodium acetate. We'll start with the lead sulfate. Sulfate ions are generally soluble, but there are exceptions, so we need to check. Lo and behold, lead 2 sulfate is an exception, and it's insoluble. So we put a solid there. Then we have sodium acetate. Acetates are generally soluble, and things with sodium, generally soluble. So this thing is super soluble. This is going to be our precipitate. How did we do with this one? Questions? If no questions, let me know that you're ready to move on. Okay. Final reaction, neutralization reactions. You're mixing an acid and a base. Remember that an acid is hydrogen plus a nonmetal, or you can have hydrogen plus a polyatomic anion. So that one we already know. For a base, you're going to be on the lookout for a metal plus hydroxide, that's the OH, or ammonia, which is NH3. Those are the reactants, acid and a base. What you make is a salt. So think an ionic compound. You also make water. If you remember nothing else about a neutralization reaction, remember that you should make water. Some of these neutralization reactions can look very similar to double replacements. It's not a double replacement if you're making water. It is a neutralization reaction. That's all we're going to say about those. I'll linger for a few seconds, and then we're going to move on to make our cheat sheet. So here are all 5 of the reactions we just covered. What I'm going to write on here is either what it is or an easy way to remember it so that you can classify it or rule it out. So it's not exactly a summary, but it's kind of the quick and dirty, what do you really need to know about these reactions so you can tell them apart. Starting with the combination reaction. We've got multiple simple reactants. You make one complex product. Decomposition reactions, it's like the reverse of a combination reaction. You're going to have one complex reactant being broken down, usually with heat, to yield multiple simpler products. Single replacement reactions. You have a metal plus some kind of aqueous solution. SOLN, that's my abbreviation for solution. You need to use the activity series for these. That's just a reminder. But the way that they look is they have a metal plus an aqueous solution of something as your reactants. Double replacement, you've got 2 aqueous solutions, and you're going to make some kind of insoluble something, usually a solid because you can't do solubility rules with gases. And you're going to form some kind of new aqueous solution. Neutralization reaction always has water as a product. That's how you can tell double replacement and neutralization reactions apart. So let me know when we could move on from this slide if you're jotting it down, because we're about to move on to our last topic, which is balancing chemical equations. So let me know when you're ready. Okay. Last topic, balancing chemical equations. The goal here is to have the same number of atoms of each element on both sides of the equation. The way that you figure that out is by counting. Revolutionary, I know. I like to make a chart that contains all the elements that I see in the equation. I use an R for the reactant side and a P for the product side. And then I count. How many hydrogen atoms are on the reactant side? 2. Same thing for the nitrogen. There's 2. That's what these little subscripts are for. How many nitrogens are on the product side? 'There's only 1 nitrogen. This 3 is only for the hydrogen. When you see a subscript, oh no, I said nitrogen. Yeah. I usually bank on somebody either mishearing me or just getting it wrong because I always want to go over that point. When you have a subscript and we're not talking about something in parentheses, it's only for the element it's attached to. That subscript is attached to the hydrogen, so it only affects the hydrogen. Now we filled in our chart. We're clearly not balanced. We have a nitrogen disappearing. We have a hydrogen appearing. Chemistry doesn't work that way. So what do? We add what's called coefficients. Coefficient is the number that you put in front of the compound that multiplies the whole compound by that number. We do that instead of changing subscripts. Why don't we change subscripts? Because changing the subscript would change the compound. So do not change subscripts. No touch, as I tell my kids when they're really little. No touch. Don't touch it. So we have our lay of the land. We know what we need to do. We need to balance both of these elements. To do that, you need the lowest common denominator. So you find a number that both 2 and 3 are easily divisible by. So 6 can be easily divided by 2 and by 3. And it is the lowest number that we can use to do this. That means on the reactant side, we're going to put a 3 in front of where we see hydrogen. On the product side, we're going to put a 2 in front of the compound that has hydrogen. Then we're going to do another table. Since we added that 3 in front of the hydrogen gas, we now have 3 times 2, which gives us 6 hydrogen atoms. We haven't done anything to the nitrogen gas, so we've still only got 2 there. On the product side, we have a 2 in front of the ammonia, which means that we have 2 times 3 hydrogen atoms for a total of 6, and 2 times 1 nitrogen atoms for a total of 2. We've got the same number of atoms on each side for both elements. We're balanced. You might see a question asking about the coefficients in the balanced equation. What that means is you're just going to list them or provide the number in front of the compound that's asked about. You always list from the reactants to the products, so left to right. We would have 3, 1, and 2. If there's no coefficient listed, like in front of the nitrogen, we don't see anything. When you're finding your correct answer or typing it in, you want to put a 1. If I asked you what is the coefficient of hydrogen gas in the balanced equation, you would tell me 3. How are we doing so far? Let's do another one. This time, you have a written description. So we're wrapping around full circle. You've got to take the written description and write out what the equation is. Then we'll take a lay of the land and see if it's balanced. Pre-make my chart here. We've got manganese metal, aqueous nickel 2 nitrate, we're producing aqueous manganese 2 nitrate, and nickel metal. Brief recap. What kind of reaction is this? Gotcha. Single. It's a single replacement. For a double replacement, you need 2 aqueous solutions for reactants. Here we've got a metal solid plus an aqueous solution. So that's going to be a single replacement. All right, back to balancing. We put all the elements that we have in our table. Notice that I didn't put NO3, the nitrate, as N and O. I kept it all together, and here's why. I see nitrate together on both sides of the equation. So I can treat it as one unit. If I saw nitrogen or oxygen in different compounds, then I'd have to separate out the nitrogen and the oxygen. But if that ion, the polyatomic ion, stays together, you treat it as one unit. It makes your life a lot easier. Then we count everything up. 1 manganese, 1 nickel, 2 nitrates for the reactant side. 1 manganese, 2 nitrates, 1 nickel for the product side. Turns out that this one is balanced. Sometimes that happens. You're asked to balance an equation. It's already balanced. So always do that first chart. Double check and make sure that your formulas are written correctly if you have to write the equation from the written description. But if it's already balanced, it's already balanced. So all of our coefficients, it would be 1, 1, 1, and 1. Done deal. Questions here? Because the next step is to have you do one yourself. So here's your problem. You've got iron, it's heated with fluorine gas, and you're making iron 3 fluoride. I'll give you a hint. Fluorine gas is one of those diatomic molecules. When you write your equation, write it as F2. Outside of that, I will give you 2 minutes to get started, and then I'll hop back in. Here we go. First part, we've got to write a chemical equation. Iron, that's just iron metal, so it's a solid. Fluorine gas is F2. We put a G behind that. And we're making only one thing. Iron 3 fluoride. What kind of reaction is this? Combination. Good. When you're doing your homework or additional practice problems, which I always post with Chapter 7, whenever you have to write a chemical equation or you're writing a description, always quiz yourself on the type of reaction that it is. It's just good practice. Now on to balancing. We take our initial lay of the land, look at things. We've got 1 iron, 2 fluorine atoms. That's the reactant side. 1 iron, 3 fluorine atoms on the product side. We are not balanced. We've got to deal with that fluorine. Lowest common denominator here is going to be 6, which means where we see the fluorine on the reactant side, we're going to put a 3. Where we see the fluorine on the product side, we'll put a 2. Always put it in front. That's where the coefficient belongs. Since we did that, we have to take stock of what changes we made. We still have one iron atom on the reactant side. We haven't touched it. But now we've got 3 times 2, which is 6 fluorine atoms on the reactant side. On the product side, we put a 2 in front of the whole compound of iron 3 fluoride. That means we've got 2 times 1, which gives us 2 iron atoms, and 2 times 3 fluorine atoms for a total of 6. Now our iron isn't balanced anymore. The lowest common denominator is going to be 2. We multiply where we see iron by 2 on the reactant side. This should be our final table. Everything should be balanced at this point. If it's not, then you need to go back and check your math. And it's a lot easier to do that when you keep track of what you did. That way you can make sure, okay, oh, I multiplied 3 times 3 instead of 3 times 2. Silly me. And you fix it. We've got 2 times 1 for the iron on the reactant side. 3 times 2 for our fluorine. We've got 2 iron 3 fluorides now. So that's 2 times 1 equals 2 for the iron, and 2 times 3 for the fluorine atoms. That's 6. Now we're balanced. Our coefficients are 2, 3, and 2. Always make sure that your coefficients are as small as they can be. They should be the lowest whole number ratio. So if you balanced it and you ended up with 4, 6, and 4, that would be correct in terms of it being balanced, but that's not the lowest whole number ratio. So you wouldn't get that answer correct. It is technically balanced, as in the same number of atoms on each side, but you can reduce that down. Any questions on balancing chemical equations? Then we have just completed Chapter 7. Couple of reminders. Mastering Chemistry Chapter 7 assignments are due on Sunday by the end of the night. You also have your Exam 3. It's on Chapters 5 and 6, available tomorrow, Wednesday, March 17th, by 9 a.m. It'll be available up until Friday, March 19th at 11:59 p.m. Make sure you start your exam by then. There's no math really to speak of, so there's no partial credit. There are a few extra problems on the exam, just as always, so you can score above 100% if you get them all right. You can also use that to say, man, I don't know this one. And you can skip a couple or just guess on a couple, and you can still get 100. If you need office hours, send me a message. Either here, you can send me a personal chat message or something like that. You can speak up, or send me a course message. Outside of that, we're done today. If you don't have any questions, you're free to go.